my name is Silva Perez. I'm the simulation specialist here at Hawkridge Systems, where I focus a little bit more on the simulation product. And I found that one of the things that I do is actually a lot of training, a lot of demoing and things like that. But within my training class, there's a lot of things that I try to add in terms of things that may not be included in the traditional manual, where tools to allow you to troubleshoot and hopefully make your simulation setup a little bit more efficient. And that's kind of what the goal is today, is showing you what's available to you in your software right now, specifically the simulation, to hopefully help you in the process of setting up your problems. So for today's agenda, what I want to do is, these are kind of, seems like a long list, but they do go by pretty fast. And it's somewhat of my top 10 things that, a lot of people may not know exist, that is included within at least your simulation standard, very basic level of simulation, which just includes static analysis for parts and assembly. So I'm going to kick off the presentation here with automatic bonding for shells. So what this is here is, if you work with shell components or shell bodies, a lot of the times a lot of my students have asked me, well, I work a lot with sheet metal, and the benefit of working with sheet metal or even surface modeling is that when you throw that into SOLIDWORKS simulation, it automatically converts the mesh type into a shell parameter. And that's probably the more recommended shell type, just because of the thin geometry that we have for that sheet metal. So that being said, for my students or customers who do work with sheet metal, they usually account for the gap they model in the gap that may be included within the actual model to account for any welding. And that's what we kind of see here in these images of my slide, where we have different scenarios, different orientations that we can apply, where you actually model in the gap or made it up to where there's a gap to accommodate the actual weld that may exist in real life. So the issue with that is, if I go into SOLIDWORKS here, I'm going to pull up this example here of this crane, and what the end goal is, if we were to manufacture this, is we're going to weld all these beams together, right? So, and the designer here actually modeled it in that way for it to accommodate those gaps. And because we know that, I'll just show you automatically here that there is a slight gap in between there. But that presents an issue if we were to try to run a study within simulation. Why? Because if we were to define an actual contact, we can define a bonded contact between those gaps, but normally what we recommend is we either model it already touching so the global bonded can take into effect. And that's what we have here. I already set up the static analysis, and the only set of contacts that we have is this global bonded, right? So what this means is, if I were to run this now, and some of you may already have the experience of already seeing what's going to happen, but you see it's running, it's chugging along, you may not know that those gaps exist, and then you get this message here saying that the model is unstable. Well, this is expected because we already saw beforehand that there are gaps within that body where there's not enough or not proper contacts applied to this body, so some of these are kind of floating in space. So what we would recommend is, there's this thing called SAW springs, where we can go into the study properties and we can specify these SAW springs to stabilize the model, and we can run it under that condition, and then we can view our displacement results and see what component is actually flying off. But the downside of that is that sometimes it doesn't always work. Sometimes you run it under that mode and it still says that the model is unstable, or something is not properly defined. So what do you do? Well, you can either do a visual inspection where, like we did, I already knew this, but it was very difficult for me to see that these actually had a gap. So you can do a visual inspection, but sometimes that doesn't work. So one thing they actually introduced within Simulation 2013 was this contact visualization plot. And if you right-click on your connections, you have that option here. And this is a nice tool because we can run a check for the entire assembly. In this case, it's a multi-body part. or we can specify specific members and see what contacts are actually available within that body. I want to run it for the entire part, and you see when it calculates here, it actually generates a list and a color code as far as what contacts are available. So if we were a little bit more familiar with the design, and we would actually clearly see that the only bonded contacts that are available are the ones where it's contacting, creating that T-shaped beam. And there's actually no contacts defined where the beam meets these beam fixtures here. So we can already see with this with this visualization plot that there may be a problem there where that's why I'm getting a models unstable issue. Well, so that's more of an aside of what we can do as far as tools. But one of the things that a lot of people may not be aware of, because it's a new feature that was provided to us in 2016. So within that contact visualization plot, we have this unrestrained or unconstrained bodies tab. You can access it on its own as well by right-clicking on connections, and you see that we have that option as well. It takes you to that same menu, except it predefines or pre-selects that tab. And it's very easy to use. All we need to do is just hit calculate, and it runs a check. It's almost running the analysis internally to see what bodies are actually flying off. So after it solves or after it completes the study, you see that it finished, it's calculating now, and it actually generates the list on this unconstrained bodies list. And this is very powerful because it actually tells us what bodies are unconstrained. So I can select on body 1, and it visually tells me, highlights the member in which the contacts have not been properly defined. Pretty much that member there is floating in free space. How do we know that? Because we see what directions they're able to move. And pretty much there are 3 translation and 3 rotational, meaning that all 6 degrees of freedom are available to move in those specific directions, and it clearly tells me that in that animation after I select that direction. So very powerful tool, minimizes, speeds up the process of troubleshooting that error message of models unstable or something is not properly constrained. You can run this under constrained bodies check, and then it'll pinpoint exactly what bodies are not properly constrained. So a very powerful tool. Again, one thing to note is that it's only available to us in 2016. So if you're kind of in an older version, you have to do the traditional, but something we'll kind of look forward to if you are considering upgrading to 2016 now. So let's go back here. And so, yeah, automatic bonding for shells, very powerful tool to help you speed up the process pretty much of troubleshooting any bodies flying off. So what else we have here? The other thing that we have is, or what I just went over, sorry, is the detecting unconstrained bodies. And I kind of jumped the gun here a little bit, but what I was getting at here is under that, the overall, how do we accommodate the overall gap size of here, you see that what we can do is we can edit the definition of that global bonded, and I can go into the non-touching face option that's also new to 2016. So when you edit the definition of your global bonded or global contact which is set to bonded, you can enable that and specify what the minimum gap thickness is as far as what that clearance is. So it can say, well, if I am already accommodating for that gap size for 2 millimeters or less, automatically define that as a bonded contact. And all I need to do is enable that option and specify what that limit is. And when I hit OK, you see that I didn't change anything to the model, where before it was giving me an unconstrained bodies. I can run this analysis here, and you will see that the study eventually should run to completion. So this now accommodates those special cases where you're working in sheet metal or in a beam structure similar to this, and you're modeling in a way to account for the actual gap size for the potential weld that's going to be there in the real life scenario. So very simple option to enable. Just go into your global contact, set it to bonded, specify your non-touching face gap clearance, and then we can now accommodate that without having to individually define those contacts for each bead. So again, therefore saving you a lot of time. So I apologize for that. I kind of jumped the gun there just because I was, it's a really nice tool here as far as detecting unconstrained bodies. But again, to recap, we can do this for pretty much shell components and these specific orientations here. Unconstrained bodies, again, to recap is, we can list out the bodies that are unconstrained and animate which bodies and what direction they're able to move. The caveat about this is, though, is that it is only available for a static study. So if you're running a more elaborate, nonlinear type of scenario there and you're still getting some unconstrained body issue, unfortunately, we don't have that tool available. So we'll have to do the traditional ways of troubleshooting that issue. What else do we have here? Mesh sectioning. This is another thing that they added within 2016 that can help you really check the quality of your mesh. Right? As it stands now, what we've been able to do is run our analysis like normal and show the mesh overlaid on top of the stress results. But we've always only been able to do that as far as the overall exterior faces of the model. So let's take a look at an example here where I have this part and I already predefined the analysis here, and I can view my stress results here, and that's fine. We can review them like normal, we can take a look at that, but eventually once the stress plot actually loads up, based on how I loaded it, I should expect to see some stresses in these fillet areas. So typically when you're running a structural analysis and you're seeing what I call like these hot spots, these stress concentrations in these areas, you want to make sure those stress concentrations are actual true values and not like some weird singularity. So what do? You end up throwing more elements within that region and see if those stress results converge. Well, you may want to know what the stress quality is around those specific stress spots. So what you've always been able to do is right-click on your stress plot and go to your settings, and we've been able to overlay under these boundary options, overlay the mesh on that body, like so. And you see that I had already applied a mesh control within that fillet, which is great. So this tells me here that I actually refined the mesh in these critical areas, these areas of concern. But what's happening if I were to do like a section view? What's going on? How good are the element quality if I were to do some type of cut section there? Well, we haven't been able to do that until now in 2016. So one thing that we can do is first we can specify the section clipping here, and very similar, or what you've been able to always do is choose whatever plane that you want to cut the model in. I can choose that plane there. But now what we have available to us is show mesh on section plane. So I can select that option, and now I can view what the mesh quality plot is, or what the mesh quality is on that cut section. And this is a very powerful tool, because when the whole point of viewing a section clipping view, as far as in the stress plot, you want to see what the magnitude of that stress is in this particular area. So you want to make sure that the overall mesh elements are actually, refined enough where that magnitude is. And you see kind of this outer section here, we have a pretty good quality mesh due to that mesh control that I created. So we now have a better view, a better outlook, and a better understanding of how good this mesh quality is, this mesh control that we applied on this specific region. And the other thing that we can do as well is related to that mesh sectioning is we've always been able to create a mesh quality plot by right-clicking on mesh, going to create mesh plot, and one of the views that we can output is the overall mesh, right? And that's what's going to show us, the overall mesh quality there. And you see I already created, or you already see where I'm getting at here, but if I were to create, go into a brand new mesh quality plot, just to kind of run through the motions here. So right click on the mesh, create mesh plot. I can view the mesh there, and it generates that quality plot. And what I can then do once it generates it there, you see all it does for this specific setting that I chose is to overlay the mesh on the body. But now I can right click on there and I can choose the option to do mesh sectioning. So when I do that, I choose it very similar to a section clipping where I can choose the plane in which I want to cut the body, but now I have this option here where I can enable, the actual overall mesh. So you see, we can get the 3D view on this as far as what the quality of that mesh is, as opposed to just overlaying that cross section. So we now get a 3D representation of that mesh quality as well. Again, all in all, just to kind of show you, how good is that mesh in those critical areas of concern. So, one of the things that are not very apparent that you may not know, but hopefully from there you find this very useful in, specifying to make sure that you refine the mesh in those critical areas. Again, one thing to note, one thing to get out of this is that it is only available with 2016 moving forward. Right. So let's kind of recap here in terms of our presentation is, we can overlay the mesh on a section clipping. We can view the 3D mesh elements on that mesh quality plot like we saw within those images there. Okay. So now, another thing that's useful that a lot of people may not be aware of, or if they are, they don't use it too much because, for whatever reason or the other, they just don't utilize it. But Shell Manager is something that they presented to us in SOLIDWORKS 2014. So it improves the workflow of how we define shells, but even more so in a large structure. So one of the tedious processes of defining a shell, if you're converting a solid to a shell with a body or an assembly that has a lot of parts, is you would have to go individually to each body and specify or convert that solid to a shell element, specify the thickness, change the offsets and things like that. But what if you wanted to make a design change where you wanted to change the thickness of that shell? Well, then you had to go back to each one and kind of define it, and it puts you more in risk of missing an actual body or accidentally changing something that you didn't. Well, Shell Manager kind of helps in that actual area there. So let's go ahead and let me open up another example here so we can clearly see how that Mesh Manager helps us here. So we have a pretty large assembly here. After I zoom out here, we have a pretty large assembly, and again, just for the for time purposes, I already generated this study, but I converted all these solids to a shell, and you see there's a lot of them. And you may be working with a lot of shells yourselves, where if you model it again in sheet metal surfacing, great, it'll take in that geometry and automatically convert it to a shell. But sometimes you model as normal 3D features, and you need to convert them manually. Well, again, to recap what we need to do, all these are shells already, but, I needed to convert that. I would need to go to each body, and, we can edit the definition of that shell. We can specify the spaces in which that shell is going to be applied, specify the thickness, and specify the overall offset. But again, kind of do that on a one-by-one basis here. So what we have available here is when we do right-click on a component, you may have noticed or you may see that we have a Shell Manager option. And when I open that, we get introduced with this interface. And what's nice about the Shell Manager is even though we selected that part as the initial component, we can pin this menu up and we can create shell definitions on the fly very similar to what you've probably been doing now. So you see that we have the traditional menu of me being able to select faces, me being able to select faces, define, if we want to do a thin or thick, we can define what that face is going to be used as a reference. Is it going to be the top surface, the mid surface? We can then even define the material and, of course, define the overall material or shell thickness. So we can generate those shells on the fly within that Shell Manager, but the beauty of the Shell Manager doesn't really come in until, in my opinion, until we define these groupings. So you see that it's optional because we can define those shells on the fly, one by one, like we always have. But I can define, create a new shell group, and it'll take me to this menu here. it'll take me to this menu here. And you see that what I can do is I can define my own shell group. And I've already created a few of them here where I can say, I can call this base rails, and you notice I can define the properties associated to that group. So I can say I want it to be a thin. I'm not going to specify a material for this for now. I want that overall base rail group to be 7.5 millimeters. Well, the other thing that I can do here as well is I can go to add another group. I can change this to 5 millimeters, right, so on and so forth. You see that I have different groups to accommodate the different thicknesses of my overall geometry. So let me go ahead and cancel this. And the beauty of this is that when you go into the shell manager, it lists out all the bodies that that you may want to convert to a shell, or that you've already converted to a shell, or you know, pretty much the properties that you want to change. So in this case, I already did that work, right? I already converted the solids to a shell, but now, because it's such a large structure, what if I wanted to change a parameter, or you know, like the overall thickness, or define an actual material for that? Well, you see all those bodies are listed within the shell manager, and they're associated to a specific group. So I specify that this specific shell body that highlights in the graphics area, I want to link that to the base lateral. And then I did that for all the other ones as well. So the beauty of this is that, what if, you know what, I made a mistake, or I just want to do a design change, and I really wanted to make all those base lateral components 6 millimeters. What I can do in the actual table is override that from 5 millimeters to 6 millimeters, but notice it didn't change it for that individual one. It's linked to that specific group, so all the other ones that have that base lateral grouping change that thickness as well. So now I no longer have to go to those individual bodies and then edit the definition and change it to 6 millimeters. I can do it just once, and it propagates to all the other components that are associated to that same group. I can do that as well by specifying a material. Well, what if for that group lateral I want to specify, you know, alloy steel or whatever it is? I can hit apply on that. You see, I don't have to do it for each individual one. It applies it for all the ones that are base lateral. So it's a convenient way for you to edit, add any property to any shell that you want to define on the fly. And we can even turn on these filters here in terms of like the overall thickness. And this is really nice too, because in this case we do have a lot of shells or a lot of surface bodies. You know, you want to make sure, in this case the way I utilize this tool is to make sure all the faces are consistent to a specific grouping. So, you know, let's say for that blue face, for whatever reason this face was a green face or didn't have a color, well, now I know I either missed that face to define it as a shell, or I accidentally defined it as another grouping. Well, I can easily go into that group, it highlights it in my table, and I can link it to an actual, you know, grouping and then change that on the fly. So it really becomes useful when we have a large assembly or a large structure that has a lot of shells. We can utilize the shell manager to be able to change different inputs at one, you know, pretty much just change one property where it propagates to the other bodies very fast, very efficiently there. So hopefully you find that very useful, and hopefully it's something that if you didn't know, you know, hopefully you can utilize that now and play around with it a little bit more. So shell manager. The next thing that I want to show you that a lot of people may not know exists is library features. So you may utilize library features in your normal modeling, where it pretty much adds a convenience factor of, well, there's a certain functionality, a certain workflow that you constantly use to design your part. So why do that for each part one by one? Why not save that workflow and then apply it for your future components? Well, it works the same way inside simulation. So what you can do is, for any fixture or any load that you may define with their proper inputs, you know, actually defining a numeric value for your load and defining a certain direction for your fixtures, you can save that and then apply it for your future components. So what I mean by that is, let me open up another example here. Where let's say I wanted to define fixtures and loads and things like that and I pretty much did that already. So you see, in this case, what I did was I defined several different loads. So in this case, for this specific load, if I edit the definition, I said that I wanted to apply a 250 Newton load, and then the same thing for these for that 500 load as well. And you see that I have a specific fixture, in this case, a fixed geometry. Right. So for this example, it may not seem too useful, but it becomes a lot useful again when you have a larger scale problem. So what you can do, for example, is for that specific load, I can right-click on that load and I can say Add to Library, right? And then it brings up this library here, and what you're looking at, this design library, is the design library that's associated on this right-hand side here, your actual design library interface here. And you may have never noticed, but you've always had an analysis library here. And this is pre-programmed within a fresh install where there's some example files there of the static analysis. There's already some load fixtures that you can apply to your bodies. But if I were to save a unique force, let's say, again, right-click on that force and say Add to Library, I want to save this under my overall analysis library here, parent folder, and I can hit OK. And when I go to my design library here, you see that I have that overall force. And I've done it a couple of times, but this one's called Force 3. That's the one I just generated. So what I can do now for any future model that I have enabled or that I want to create, I can simply drag and drop that force anywhere in the graphics area, and you see that that load is already predefined, right? And then all you have to do is select the faces in which you want to apply that load, right? So it becomes more of a convenience factor again when you have a large scale model and you don't want to necessarily keep right-clicking on that body or on external loads and then selecting all your faces. If you're comfortable, if you apply this in your design process, it may be a little bit more efficient for you in the simulation side, but it's just letting you know that we do have that option available. You see that I created the same workflow here when I created the fixture. I right-clicked and say Add to Library, and I saved it under the design library, and I can throw that in there as well. I can throw it in the graphics area, and you see that I can, and even saved in this case, all the edges of that fixture. So I can create all those fixtures or kind of just a quick drag and drop and then redefine them automatically, right? So nice little convenience factor that we have available to us that's always existed, you know, and something that's very similar in our design process as well. So going back to the overall presentation, again, all you have to do to add a library is right-click on that sim feature and then save it in whatever folder structure you want. And then we can apply that for future models. And that's kind of what you're looking at there in the images, is being able to throw it into the graphics area and then make the proper selections within the actual unique model. So I just got a question here. Good question. Can I save certain plots within the model? I want to say I can take a look at this right now, but those are going to be unique to the actual interface. So it's just going to be embedded in the normal result file. You see here when I right-click, there really is no option there to save it into the library. So unfortunately, when it comes to those results, because they are unique to that specific body, we can't use that. So hopefully that answers your question. If not, go ahead and feel free to send a follow-up question there as well. But this leads me into my other, did you know this existed topic, which is submodeling. And it's something that they introduced in 2013 as far as its capability, but it's a nice way for you to break down the overall global assembly that you may have run and focus on a unique component and run further refinement on that body. So what I mean by that, it really becomes beneficial when it's a large assembly. And that's what we're going to run here. We have this frame, and I define the proper fixtures, define the loading condition, but I see that I get a lot more stress on this specific component here. So now my attention is focused on that component where I want to refine the mesh, get more accurate results by refining the mesh on that individual member. Well, if I refine the mesh, add a mesh control, that's fine. But if I do it within that top level assembly, that means it's going to mesh, the entire assembly and rerun the actual assembly. But what I can now do with submodeling is kind of take that component onto its own study. It'll take in the effects of how it was fixed or how it was restrained relative to the global assembly. It'll take over, bring over your forces and your fixtures, and all you would want to do is just refine the mesh on that individual component, therefore saving you on computing time and still getting what those accurate results are for that individual component. So how does it work? So you see that I ran my overall top level, my master simulation study, if you want to call it that. And what I did again was I defined my fixtures on the ends, I defined my loads, but now I want to focus my attention more on this member. Well, and when I say focus my attention, I mean I want to add a mesh refinement on that member, but I don't want to necessarily run the entire assembly there. So what I can do is I can right-click on the body, I can right-click on the overall study, and I can choose this option here to create submodeling study. So when I select that option, it gives me this message here as far as what advantages that submodeling has and what are some of the limitations. So there are some limitations to this, right, because we are kind of isolating that component. One of the things that really stands out to me is that the parent study, so the master study, can't have any no penetration contact kind of defined within this while we take that into a submodel. So right now, we assume that everything was bonded in order for this to work. So kind of taking a look at that list and seeing what works and what doesn't. It doesn't apply for every condition, but again, the point of submodeling is once we hit OK, we can then choose what member we want to isolate. And in this case, I can choose this member here, and all I need to do is just check, hit the check mark on that box. If it makes sense, if things were connected, I could even select these two components as well and kind of isolate those on, not just on an individual basis. So in this case, I want to select that component, and when I hit OK, it brings that individual body into a unique study. So let it process here for a sec. And what I want to show you is that the overall setup is overall going to be defined. And what's nice about this is that it creates its own individual configuration as well. Like it creates a derived configuration is what I say. So you have your top level configuration. You see that I ran a couple of these, and we have the default submodel for this specific component. But you see, what we can then do is we have that individual component. Under fixtures, we have this displacement from parent master. So we don't necessarily have to define any more fixtures because it's already taking in that data from the original master. You see that it should have brought over the loads as well. But in this case, if I kind of go over to my submodel here and activate that configuration, you see that we kind of control, or we specified what loads we wanted to transfer over. But again, the main point is now being able to add a mesh control, add further refinement on that individual component. And when I run this, you'll see that it's going to run the analysis for that individual component. And it may need to update if you made a change into the master model, so it'll run both. So you see it runs the master, and then it'll switch over to the submodel, and then it runs it as well. So you see that we still get the loading bar there. And I didn't add a mesh control in this case, but that's what we could do within the submodel, is we didn't need to define any fixtures. We were able to bring over the loads as well, and we can add a further mesh control, and it takes into account as if it was still attached to the frame. So we can focus our attention more on this individual body and getting at a more accurate stress result due to their mesh refinement and not having to run and mesh on the global scale or on the master model. So again, being more efficient, saving more time on the overall simulation study. So hopefully something there that you can utilize moving forward here. So again, more accurate, more efficient analysis on areas of interest. Similar to simplifying or kind of saving time, especially computing time on an analysis, I'm sure we've all gone through it, where we kind of generate this complex geometry. Well, a lot of the times, and where it doesn't apply for every condition, there's certain things you need to consider. But one example I like to use is, well, what if you modeled something that's symmetric about a cutting plane, and your loads and your fixtures are symmetric about that cutting plane as well? Well, why not cut the runtime in half by physically cutting the model in half and specifying that you have a symmetry condition within simulation, right? We have similar capabilities as well in something called 2D simplification. So 2D simplification kind of has three different categories here, and that's what you see here in this PowerPoint image. We have a plane stress, plane strain, and axisymmetric. So you kind of view my bullet points there. I know it's a lot of text, but you may have a situation where you have some extrude where the stresses kind of going normal to the screen, if we were looking at a front plane, can be almost ignored because you wouldn't expect to see a lot of stresses in that direction. So, and that's what my first bullet is saying is, for plane stress, one dimension in the model is much smaller than the other two. So if you look at this extrude, the depth of that dimension is a lot smaller than everything else, where we wouldn't really see too much activity there. So the normal and shear stresses associated with that small direction, we're assuming that are zero. So there are some assumptions that we're making within that 2D simplified, but where you would expect in that example at least, the stresses that are going to be more important to you are the ones in the plane direction, which is why it's called a plane stress. Similarly to a plane strain, or similar to a plane stress, we have plane strain, where it's almost like the opposite effect, where one dimension in the model is much larger than the other two. It usually comes down to those long geometries, kind of like what you see here, like a tube or some kind of piping, and you can literally take a slice of that model anywhere within that long model, and the stresses or the deformations are going to be the same, across the entire geometry. Again, assuming that the loads and fixtures are symmetric or equal across that entire body. So if you have like a distributing load, that may not be a good case to utilize a 2D simplified geometry. And then if you work with like revolved geometries where, again, the pressure is symmetric or axisymmetric across an entire face, we can almost revolve those boundary conditions and assume that everything's going to be uniform across that revolve, and then simplify it and taking a slice of that model and running the analysis in a very quick fashion. So here are some examples before I actually show you the interface where it's located, but really nice example here. This is a plane stress example where we can take a slice of that model where we're assuming the depth of that geometry is, you're not going to see a lot of stress activity. So we can actually still get stress results off that 2D simplified case. In a plane strain scenario, again, usually intended for long, slender geometries where that stress is going to be uniform across that entire length, we can take a slice of that model and simplify that process where we're not necessarily applying the loads onto the faces, we're now applying the loads onto those edges. Same thing with an axisymmetric where, I want to clip something into that overall extrude feature, and I want to focus my attention in that area. I don't necessarily have to model the entire 3D or run the analysis on the 3D geometry. We can just take a slice of that, look normal to that, and see what those stresses are. So how does that interface look like, and how does it work? Well, that's the overall gist of what we need to consider for 2D simplification. But, oops, sorry about that. Let me go into my SOLIDWORKS here real quick. And let me show you a 2D simplified example here. So I'm going to start off with the 3D model, And all I want to do, and this is a nonlinear analysis, but all I want to do is see what the stresses are of those actual clips snapping into that lid. So I'm going to add some compressive force to actually snap it into that component. But you notice that we have a revolved shape where it doesn't really matter, because it is axisymmetric, do I really need to run the entire 3D model? That's a pretty complex model in a nonlinear sense, because there's a lot of contexts that are changing as the load's being applied. So what we can do is I can generate a new study, and that 2D simplification is available to us under a static analysis, thermal, and even a nonlinear. And you notice that for those study types, I have this use 2D simplification option. And when I enable that option and then hit OK, you see that I can choose what study type I want to run. And it's associated to whether you have a plane stress, a plane strain, or an axisymmetric. And what's nice about that is we have an animation that's associated to that. So you see in that wrench, the overall thickness of that, we don't really care about that. We wouldn't expect to see too much stress in that direction, only in the plane direction, so we can take a slice of that model and apply our geometry. Same thing with the plane strain, usually more for long components. Anywhere where we slice the model, those stress results are going to be uniform across that. And then we have axisymmetric, where we just choose what that cutting plane is, choose the axis of rotation, and you see, the results we get, and we can kind of revolve that in that fashion. So really nice animations to kind of show you that. In this case here, I already have it defined, and you see that we get something like this, where just imagine these two components being revolved around that axis, we would get that overall 3D geometry. The way we set up the problem is very similar, if not easier, than what we would have to do in a 3D sense. We still need to define the material properties. We still need to define the fixture. In this case, if I edit one of those fixtures, instead of me having to select an actual surface face, I'm just selecting the overall edge. And that's representing that if this was revolved, that entire face is being selected. And the same thing applies for my load conditions here, where we actually didn't apply a load condition, but the same thing would be the case as far as me selecting the overall edges. In this case, I applied a prescribed displacement, where normally in the 3D model I would specify select that face. Now I'm selecting the overall edge. So the process almost becomes a little bit simpler, and the processing time, the computing time, becomes a lot faster as well. We even have the option to define a mesh control on fillet edges or faces and things like that, where I can say, well, my area of concern is along this fillet. Again, I can select that edge as well. So once I define my study like you normally would, you can run the analysis, and for this nonlinear case at least, we can see it kind of snap in and get an overall understanding of where those stresses are, so we can eliminate having to define all the context for all those 3D faces. We can simplify it with this 2D simplified analysis. So you see, we still get the results that we want. We're getting the stresses, and we're able to see the stresses in the areas of where we would care about. And when I snap that in, once it completes, we can review the results like normal. In this nonlinear case, we can still view, what the stresses and displacements are, factor of safety, except we don't initially have the 3D geometry. I always make this joke, well, what if you needed to create a report, present it to your boss? Your boss is going to look at this and say, well, that's not the actual physical geometry. Well, luckily for us, simulation thought of that as well, where we can edit the definition of that stress plot and view it as a 3D model. And you see, all it does is it revolves the actual 2D simplified component. So we get a better representation of how it's actually going to look in real life. You see that it cuts off the section there automatically. We can close that off if we edit the definition there, just to show you what that cross section is. But we can go to the advanced options and say 360, right, and it'll close it off. But again, a very complex problem drastically simplified with that 2D simplification process, right? So very powerful tool here, right? And hopefully something that you can utilize within your future studies. Again, it doesn't apply for all of them, but you kind of get, hopefully you have the general idea of, when you can apply these to kind of make your life a little bit easier. Okay. Well, kind of running towards the end here, I just want to show you quickly some of these other options that are available to us to kind of help in our overall setup process and our design process as well. And I'm going to start off here with the Design Insight Plot. And a lot of people, I haven't seen a lot of people utilize this, but it's a way to show the regions in which the areas of the model where it will see a lot of the load, therefore potentially excluding areas where it won't see the load, and then you can make the decision of, well, if it's not going to see a lot of the load that I've applied in those specific regions, I can essentially remove some of that material, saving on material cost, right? So what I mean by that is, if I show you this example here, where I ran an analysis on this bracket assembly where I applied a load on that spherical shape, and what I want to do here is now take a look at my stress results. That's fine, I get the stresses in the areas of where I would expect them, but what if I wanted to ask myself, is there anywhere within this bracket that I can remove some material where it won't really affect the stresses of that geometry or affect the overall design? And that's where the Design Insight Plot comes into play. So if I right-click on my overall study, if I right-click on my results, I can create this Design Insight Plot, and you see that you can read the message here, and it says, adjust the slider to plot a continuous path between the loads and the restraints. The translucent portions of the Design Insight Plot carry the applied load less effectively than the solid portion. So pretty much what I can do is I can specify, at one extreme, where the loads are not really playing a factor at this point in time. But if I gradually increase where the loads, or where this particular assembly is going to see those loads, the areas in blue are the areas where it's seeing those load conditions. The areas where you can see through them are pretty much the areas where it won't see most of those load conditions based on our setup. So pretty much what you always want to do is kind of set it to an all or close to all condition, and you can see, well, in this area here, I can get rid of probably a good portion of my bracket within this region. Just in the simple fact that it's telling me under the Design Insight Plot that in that general area, it's not going to take in or see a lot of the load that's being applied within this overall setup. So it's very similar to an ISO plot, where in an ISO plot, when we take a look at our stress, we can go into ISO clipping and we can say, show me everything above 120, or show me everything below, I should say, 120 MPa. So where in an ISO plot, you're actually specifying, specific to a plot, what your areas of interest are, and you can say, pretty much show me everything below a certain stress value or certain design constraint. You eventually see, the areas in which, very similar, I kind of have it opposite here, but you can see it works very similar in the way of, well, where are the areas where it's not going to see most of the stress? We can then utilize this plot to kind of cut out some of these regions. But more specifically, a Design Insight Plot does a very similar functionality here, where, again, it shows you the areas where it won't necessarily see too much of the load. And when we apply, quote unquote, all of the load, we see we're left with certain regions in which we can cut out and save a little bit on material. So a very powerful plot type that's available to you after you run an analysis. The other thing that we have available to us here is selection sets. Selection sets is a nice way, something they introduced in 2015, and they showed it more as a design integration, not necessarily in simulation, but not a lot of people are aware that you can utilize that within Sim. So what I mean by that is selection sets are a way for SOLIDWORKS to save certain selections that you select on your body, right? So one of the issues here that a lot of people come across, and I've come across, is defining contacts in an area where you can't easily select a face. So let's say I wanted to find a contact between this pin and the face that it's actually touching. Well, there's a lot of different ways we can do that where, we can define our contact, and we can select this face here and then do some kind of select other, right-click in that region, and kind of get that general idea of where that selection is. But sometimes it's not too clear in terms of what you're actually selecting. So in this case, the one way to accommodate this is creating an actual exploded view. So I can create an exploded view, define my contacts here, and I can select this face and then select this face, right? So that's one way to do it. But the other thing that we have available to us is, well, what if we pre-select all the faces that I'm potentially going to be selecting a lot? What I can do is let me go back to the model so we actually see this a little bit clearer. What if I select this face? I can right-click on that face and I can say Save Selection. I can select this face as well and do the same thing. And you may be asking, well, where are those saved selections being stored? So, and then in this case, I can multi-select these two faces. Multi-select these two faces here, right-click and say Save Selection. As far as where they're being stored in my feature tree. And you see that we have 3 unique selections here. All right, so, and didn't properly, or at least I didn't, let me select this face here. Let me do them individually, actually. So you see that we have that selected face, or it should just be selecting that individual face. But now what we can do within that study is when I go into, let's say, my contacts, right-click, connect, or contact set, I can split my menu here, and I can say, go into my selection sets, and I can easily select certain selections here. Not really working for me here. Let's try fixed geometry. All right, you guys are going to have to take my word for it here. Unfortunately, it's not grabbing the selection. But what I should be able to do, or what I should be able to see, is when I go into a load or a contact, instead of me having, the issue of, let's go ahead, if we go back to the collapse state here, the issue of me going to an actual contact set and not easily being able to select those faces, I can utilize those selection sets and, have it predefined or have it select for me as far as, that saved selection. Unfortunately, it didn't work out for me, but I promise it should work. I've tested it before. It's just not cooperating for me here. But very more efficient way to define those contacts and those load conditions, because you've already saved out those selections, those face selections there. So let me kind of show you the last thing here, which is the trend tracker, which is a nice way to be able to define like a baseline study and then compare certain results based on any changes that you've added to the model or overall sim setup. So what I mean by that is I ran this analysis here, and you see we have our stress displacements already defined. What I can then do is set all these parameters, or these results, as my baseline. And when I right-click and say create trend tracker, you see we don't have anything really defined. I can right-click on that trend tracker, and since I already ran the study, I can set this as a baseline. And it tells me what the overall mass is. So when we view that here, sorry, let me move my menu here. We have one point within that baseline. If I view my stress here, we have some point within there. So it's just logging what that stress value is at that, first iteration. So what if I then change this, or change my value here to not 7,000, but let's cut this in half, right? So let's just do a simple divide by 2 and hit OK, and then rerun that. You see that it changed the trend tracker from my baseline to iteration 2. Well, what if I apply or suppress gravity onto that and see how that plays a role, well, I can do that as well. So I'm changing certain parameters of my setup. I can even link this to a geometry change as well. If I then actually made that cutout within that bracket, what are those stress values or these plot types going to do when I make that change? So now what I can do is I can view what the overall stress was, and when I view that plot, here, oops, let me bring it over again, sorry. When I view that plot, you see that for that baseline, we had a max stress of, a little over 140. When I divided that load in half, it dropped it all the way down to a little bit above 70, and then gravity didn't really play a role either. So you can change all these parameters here. You can view the same thing for displacement, where you can look at the trend of what's happening when you make those sim setup adjustments, right? And the beauty of this is, well, what if you're like, okay, well, that first iteration showed me the best stress or showed me the max allowable stress that I'm comfortable with. Well, let's revert back to that option here. So I can right-click on Trend Tracker, and I can say, I can view the gallery, or I can right-click and say, I can restore a model to an actual iteration, and I can specify it to a specific baseline or any iteration that I apply. So if I want to revert everything back to the baseline, I can hit OK on that. We just want to accept that there, and then eventually it'll bring everything back to the original settings where, in this case, it brought that load value back to 7,000 as opposed to what I had changed it after. So in this case, it makes it a lot easy to see what those changes are and then, kind of revert back to those actual points there. So we have a couple questions here. Can we change the location of the stress probe for that tracker? We can, so I'm assuming you're talking about the stress probe in terms of the actual annotation that's being applied. Not necessarily. The only thing that we can change are the parameters of that overall setup or the actual model in itself. So, parameters such as the loads, the fixtures, or the connections, things like that, those are the things that we are able to change, and it'll reflect within that Trend Tracker. I had another question here. I think it was reverted back to the section view. Is the section plot, in section plots, is there a way to remove the wireframe and the hidden part of the section view? Actually, I may have to go back and kind of go back to you on that question there. I want to say that we can, but I would have to specify and actually look for that location there to hide it there. But I want to say we can remove the wireframe of that, but don't quote me on that until I test it. But hopefully, going back to the original case here of the Trend Tracker, hopefully you see the benefits of that. Again, we just right-click on our study, add the Trend Tracker, we set our baseline, and then we change our parameters, and it ultimately saves those components. So definitely let me know if you have any questions about this. We kind of went over a lot, but hopefully you see that there's a lot of hidden gems within SOLIDWORKS simulation that you may not be aware of or that you didn't know, and hopefully this presentation helped with that. So definitely let me know if you have any questions. Feel free to ask those questions within the webinar interface. If you want to take it offline, you can email me at silviop@hawkridgesys.com. But I just want to thank everyone for attending, especially around a couple minutes late here. But just want to thank you guys for attending here. We do record these webinars, and you should see them later on in our website. So definitely let me know if you have any questions there, and have a good day.